This is the third session on quantum sensing today. Earlier on Tuesday, we had atomic gradiometers. Then yesterday, we had OPMs, atomic vapor cell-based quantum magnetometers. And today we will again discuss an entirely different type of quantum sensor, Rydberg atom-based sensors for measuring electric field. And Bonnie Marlow will take a different approach here, also telling you about the systems engineering perspective. Very happy to have Bonnie here. She is the group leader of the quantum sensors group at MITRE. She's an expert on Rydberg atom-based quantum sensors and previously worked at the Joint Quantum Institute, University of Maryland and NIST on squeezed light for precision metrology. And she obtained her PhD from Duke University, specializing on nonlinear optics in cold atoms. And we're really looking forward to hear more about MITRE, Rydberg atom-based sensors, and especially the systems engineering approach.
All right. Thank you so much, Marlow. I'd first just like to express my thanks to the organizers for inviting me to speak to all of you today. I know that you're learning a lot about different quantum technologies and concepts in this program. So as Marlow said, I'll really be focusing specifically on the area of quantum sensing, which is the most advanced subfield of quantum science to date. And so I'll specifically be describing a methodology which is based on concepts from systems engineering to support advancing quantum sensor technologies from laboratory systems to practical devices. And so I know that many of you are students who are just starting research, or maybe you're thinking about starting research in this field. And what I hope you'll take away from this talk is that you can really make an impact today in helping to support the whole end-to-end research and development pipeline for these quantum sensor technologies, and I'll explain how. Before I dive in here, I first just wanted to give a quick overview of the company where I work. So I've often heard MITRE called the biggest company that no one's ever heard of. So many of you have likely never heard of us before. So MITRE is a not-for-profit corporation that operates 6 federally funded research and development centers, or more commonly known as FFRDCs. And we use those FFRDCs to support different organizations across the US government. And then we also operate a support organization, which we call MITRE Labs, which is where I sit. And that's where we do a lot of our own independent research, as well as a lot of the technical work that supports the different FFRDCs. So MITRE has about 10,000 employees or so that work around the world at more than 65 locations, supporting our military and other government organizations. A lot of people think of us as a systems engineering company, and we certainly do a lot of systems engineering, but we also work more broadly than that. And as part of that, we work to apply concepts from systems engineering to research and development. So today, my goal is to describe the systems thinking methodology in the context of quantum sensing, and to describe the value of bringing an interdisciplinary perspective to the quantum sensing research and development pipeline. So I want to start first by just giving a short overview of the field of quantum sensing. So my favorite definition of quantum sensors, which I stole from a colleague, is that quantum sensors are devices that leverage quantum phenomena to measure fields, forces, or time. And so at the top here, I show a number of different types of quantum sensors. So this is not a comprehensive list by any means, in that it doesn't list every single type of quantum sensor in existence, but it does list some of the select quantum sensors that I expect will have high impacts for both national security applications as well as for the private sector as they're developed further. So there are quantum sensors that can measure different types of acceleration, including quantum accelerometers and gyroscopes for measuring inertial acceleration, which can be used for inertial navigation, as well as quantum gravimeters and gravity gradiometers, which it sounds like you heard about earlier this week. Those measure the local acceleration due to gravity, and they essentially can be used as passive mass estimators. And then there are also quantum sensors that can be used to measure electric or magnetic fields. And then while they're not really sensors per se, atomic clocks are often lumped into this quantum sensing category because they have essentially similar core technologies and measurement procedures, even though they're sort of effectively sensing internal atomic dynamics rather than sensing external fields or external forces, as is the case with these other technologies. So in general, the motivation behind building quantum versions of various sensors is that compared to traditional classical sensors, quantum sensors offer the potential for improved performance in some key metric. It might be better sensitivity or better accuracy, for example, or they offer what we call smaller swap or smaller size, weight, and power, or they might offer both. And so there are different what we would call value propositions for all of these different sensors. And I'll give some examples a little bit later on here as well. So what I'll be doing today is doing a little bit of a deeper dive into just one of these quantum sensors, specifically this type of quantum electric field sensor, which is called a Rydberg atom electric field sensor. I'll do a deep dive into that one just because that's the type of sensor that I'm developing here at MITRE. But if any of you have any questions or just want to learn more about any of the other sensor technologies listed here, I'm more than happy to chat about them during the Q&A. Of the sensors that I listed on that previous slide, there are three primary types of underlying core technologies for these quantum sensors. And by that, I mean the technologies that are actually acting as our sensing elements, the things that are actually measuring those fields, forces, or time. Those sensing elements are primarily either atoms, defects in solid state crystals, or superconductors. So a few of these systems have been commercialized or are starting to emerge on the commercial market. So here I'm showing just a few images representing some select commercial versions of these sensors. The full sensor system houses, of course, not only those core sensing elements, but it also houses supporting electronics and other component technologies that enable preparation and readout of the measurement. So in general, every quantum sensor follows roughly the same kind of high-level measurement procedure. So we typically start by preparing our sensing elements in some way. So for example, with atomic sensors, we often use lasers to prepare the atoms in a certain energy state. Then we allow the system to evolve during a chosen measurement time. So for atomic magnetometers, for example, we allow those atomic states to evolve under the influence of some external magnetic field that we're trying to measure and characterize. And then as a final step, we need to read out essentially how the state of the system evolved over the course of that measurement time. So for one of these atomic sensors, for example, we would use a photodiode to detect an optical field that has passed through the atoms. And because that optical field interacted with the atoms and their new energy state, the properties of that optical field very conveniently carry information about how that atomic energy state changed during the course of the measurement. And we can relate that back to obtain information about the properties of the magnetic field that caused the change in that energy state. So that's just the kind of overarching general measurement procedure for reading out information using these sensing elements. So quantum sensors today have a relatively wide range of technological maturity. So I showed you on the previous slide, a few pictures of commercialized systems, but there are other types of sensors that are for example, very early research stages. There are some that are in the applied research stages as well. So this bubble chart is one that I originally drafted for an organization called the Quantum Economic Development Consortium, or QEDC. If you haven't heard of them yet, I suggest you look them up. They have some great events for students to share their work with the broader quantum community. And they also post things like internship and job listings as well. So I participate with them on one of their technical advisory committees, and I helped them plan a workshop where we basically showed this bubble chart to a number of different stakeholders in quantum sensing, including academic researchers, industry developers, stakeholders in government, and we asked them, is this right? How do you assess, the relative potential impact of each of these quantum sensors? Should we move any of these bubbles left or right on that maturity scale? And what I'm showing you here is the final version of this bubble chart that has taken into account inputs from that broader community. So I want to, caveat showing you this by saying that there are always limitations to generating this type of chart. So, for example, there are newer versions of those chip scale atomic clocks that are currently in relatively early research stages, which aren't shown here. And there, of course, could always be, unforeseen developments in these sensors themselves, or even in, competing classical sensor technologies that might shift, the projected impact levels up or down over time. But for now, this is essentially, one informed, albeit still notional, representation of the potential impacts of some of these quantum sensor technologies. So I won't go through every item on this chart, but I'll note that the sensors that were ranked as having the highest potential impacts included small size atomic clocks, which might be used in applications such as maintaining precision timing for low Earth orbit or LEO satellite networks, or just in general for maintaining timing if GPS is degraded or unavailable. And then also another that had a very high projected impact are these atomic interferometer-based inertial sensors, which may be used to support future inertial navigation systems with the potential for improved long-term stability and accuracy compared to classical devices. And then additionally, there are these different electric and magnetic field sensors that were also ranked as having sort of moderate to high impact for applications like magnetic anomaly detection or magnetic field aided navigation, for example. But overall, the main items that I want you to take away from this chart is that there are many different types of quantum sensors with many different potential applications. Some quantum sensors have successfully been commercialized and deployed for select applications. There are other types of quantum sensors that have a long road ahead of them before they'll be used in practice. And what I'll mostly focus on for the rest of my talk is that long road, is that full research and development pipeline. And I'll be giving you my perspective on how to make that research and development pipeline more efficient. So when I first came to MITRE and was thinking about how to motivate starting a new research program in quantum sensing, I had to think differently than I did when I was doing research as a grad student and a postdoc in academic environments. In academia, you really want to explore the fundamental science. You want to understand the realm of the possible for a given technology or capability. So academia is largely responsible for what we call low TRL research, where TRL stands for technology readiness level. So this TRL scale that I show at the top here is widely used in the government to assign technological maturity to a given technology. So at the low end of the scale is basic or fundamental research. And at the high end of the scale is where we're generally talking about commercialized technologies. So in academia, you're really doing research that is essentially setting the stage for which technologies or concepts can move on to this higher TRL research and development. So coming to MITRE then, which operates these FFRDCs, and so we're operating in this mid-TRL range of applied research, where we have this goal of showing technology validation outside of a lab. So at MITRE, I had to take a different approach to motivating my research than I did in academia. I had to really fully analyze which applications, which specific use cases I was targeting before I could even start experimentation. And so this was a really completely different research methodology than what I was used to in academia. And yet academia, I was used to having, flexibility in what I could explore, what questions I was interested in answering in the lab or in, some of the theoretical work I was doing. But having, navigated the shift to a more application-focused scope to my work, it's something that I now really appreciate as being very important for successfully transitioning technologies from the lab to practical use. And so what's I think is clear just from showing you this TRL scale is that there are multiple types of organizations that are all critical to successful technology development and deployment. And so what I advocate for within the field of quantum sensing is the idea that because all these different organizations play a role in technology development, they should ideally be collaborating in parallel rather than in series throughout this whole research and development pipeline. And that interdisciplinary approach is something that we work to apply in multiple fields at MITRE. But here I'm just going to be giving some specific examples regarding applying that concept to quantum sensing specifically. So our goal is to help advance these quantum sensing technologies that have the potential to have high practical impacts. So the challenge is overcoming what's often called the valley of death. Now, this is a very highly notional curve. It's definitely not valid for the maturation of every technology. But in general, this is how funding often evolves in technology development. So the horizontal axis is that technology readiness level scale that I showed you on the previous slide. And the vertical axis is the notional investment level. So typically there is public or government funding for early research. And then once a technology has been proven to work, there's more significant investment from the private sector, like venture capital firms, for example. But there is notoriously very limited funding from either the government or from private investors in this mid-TRL range, where we are actually trying to demonstrate the practical utility of emerging technologies. And for any startup companies that are developing a new technology and trying to survive this transition from an early prototype to a proven capability, this mid-TRL range is what's known as the valley of death because it's where the development of many technologies just stops. In some cases, it's because they failed to show the potential for practical utility. So there's no need to continue developing them. But in other cases, it's because the funding just dried up. So what I'd like to do is pose this question of, how can we successfully transition quantum sensor technologies from early research to commercialized solutions that have real impact. So my hypothesis is that adopting a systems engineering type approach across this whole research and development pipeline leads to more efficient and more successful technology development. So the R&D pipeline here includes, both researchers and manufacturers of the component technologies. It includes the developers who actually, work to build practical versions of the sensors. It includes the systems integrators who take that new sensor and integrate it into a larger platform that will actually use or deploy the sensor. And then finally, the actual consumers or the end users who will use the sensor on a day-to-day basis. So what is this systems engineering approach that I'm proposing for this pipeline? So I'm going to give you sort of the formal definitions first, and then actually go through an example that I hope will be more useful. So I'm going to define a system here as a combination of elements that together produce a capability, which is required to meet a need. And I have shamelessly stolen this definition from NASA because it's my favorite definition of a system. It's definitely an elaborate definition of a system, but it's one that is really most appropriate in this context. So then systems engineering, we define as an interdisciplinary approach for the design, realization, technical management, and operation of a system. And I think you can see that, the definition of systems engineering is actually sort of mirrored in this R&D pipeline. There is early stage design from the researchers, there's realization of the system by the manufacturers, management of deploying and using the technology by the system integrators, and operation by the end users. So what does this interdisciplinary, systems engineering approach look like for quantum sensor research and development in particular? Well, we certainly need to start with quantum physicists for the research, but then we also ideally want those physicists to be collaborating with stakeholders across this whole pipeline, which includes engineers, it includes signal processing experts, systems integrators, operational experts, and end users. So all these different experts play a role in developing and deploying these technologies. So what I advocate for is that there should be as much communication as possible among all of these stakeholders, starting as early as possible in the research and development cycle. So, and that includes starting with all of you, starting with the students who are proving out concepts in the lab or in theoretical work that you're doing. That's the best way to identify problems early on and to help ensure successful development of a technology that can make a real practical impact. So in this systems engineering approach, we actually ideally want to formulate our research problem by first communicating with the end users. So we first want to ask, who the stakeholders and end users are for this technology. What do they need that they don't have today? Then if we can establish that need, we want to ask what the systems integration requirements are. How big can it be? How heavy can it be? How ruggedized does it have to be? Does it have to operate on a fighter jet or a satellite, or can it just sit in a big air-conditioned building on the ground somewhere? And then what about ease of use as well? That's a big one for us here at MITRE, because in many cases we need to think about how to make something that is operable by someone in the military who is not an expert in the technology. So how do we ideally, just make an effectively turnkey version of a quantum sensor? It's a big challenge. We also need to figure out what performance metrics are required to meet the need. And that comes back to the value. So if the need is to build a more accurate sensor, then we have to make sure that the sensor is demonstrating that improved accuracy in every stage of the research and development pipeline. And then another key question relates to component technologies. Do the requisite components already exist? Or do we need to facilitate or advocate for funding to develop those as well? So just as one example, a big challenge with atomic sensors is that they need lasers to work. But lasers are often relatively fragile. They perform much better in a temperature controlled lab than they ever will outside of a lab. So identifying those types of challenges to deployment early on can help accelerate this whole R&D pipeline and get these technologies out the door sooner. So in this last portion of my talk, I'm just going to dive into a specific example of how we applied this systems engineering approach to research and development of one specific type of quantum sensor here at MITRE. So for the past few years, we've been developing these Rydberg atom electric field sensors at our headquarters in McLean, Virginia. So this is a type of electric field sensor which is based on highly excited atoms known as Rydberg atoms. So we can excite an atom to these very high energy Rydberg states by allowing them to absorb some energy from lasers. And when we do that, what we're actually doing is essentially pushing the valence electron, or the outermost electron of these atoms, outward, so that it's actually physically much farther than usual from the rest of the atom. And by essentially stretching the atom and making it bigger, we've separated that negatively charged electron from the remainder of the atom, which is positively charged. And what that gives us is an atom that's essentially behaving as a minuscule electric dipole, which we can use to sense electric fields. So then to make a full electric field sensor, we excite many Rydberg atoms. And then by probing them with light, we can actually measure what happens to them when an incoming radio frequency signal passes through them. And this still follows that same overarching quantum sensing measurement procedure that I described earlier. So first we prepare the atoms by exciting them to those Rydberg states. Then we allow them to interact with some RF field that we're trying to sense, where that RF field modulates those little Rydberg atom dipoles, which in turn actually modulates both the amplitude and the phase of the optical fields that are passing through the atoms. And then by detecting one of those optical fields on a photodiode, we can read out directly the properties of that RF field that interacted with the atoms. And so when I describe this technology to people in the RF community, I show them this schematic on the bottom, and I tell them that you can essentially just think of this as an emerging sensor technology that can replace both the antenna and the front-end electronics of a traditional receiver. It happens to be a quantum sensor, but what really matters is that it offers some unique capabilities that are distinct from traditional antenna-based receivers. So I also always emphasize that this sensor will, it'll certainly never replace all traditional antenna-based receivers, not even close, but it does have some unique characteristics that are expected to enable new capabilities for certain application spaces. So what are some of those unique capabilities? Well, firstly, these sensors have a very small size sensor head, and because they have a completely different principle of operation than antenna-based receivers, the physical size of the sensors does not scale with the wavelength that they're sensing. So this is in contrast to traditional antenna-based receivers, where, as you can sort of see on the bottom here, as we move to lower and lower frequencies, across the whole electromagnetic spectrum, we're moving to larger and larger wavelengths. And antennas typically become larger and larger and scale with that wavelength because their physical size is correlated with the wavelength in order to have enough gain to measure a good signal. So for the frequencies that we typically use up around, say, GPS and Wi-Fi and Bluetooth, which is typically around sort of the low gigahertz frequencies, those signals have wavelengths of only a few centimeters. So we can detect them very well with antennas that are correspondingly close to those centimeter scales. That's the size of an antenna that you have in your cell phone is just is relatively small on that centimeter spatial scale. And then as we move to longer and longer wavelengths, lower and lower frequencies, antennas typically become progressively larger. And if we want to be able to sense across multiple frequency bands, using classical technologies, we would typically need multiple sets of antennas and multiple sets of front-end electronics to be able to sense such a wide band. So the Rydberg atom sensor, in contrast, has a fairly small size sensor head that's capable of sensing across the whole spectrum shown here. And they're also highly selective at some of these higher frequencies, which means they do a really good job of rejecting noise outside of a narrow spectral window, which is great for trying to communicate in a noisy environment. So we recognized early on that these sensors were unique, but before we could even start research, we needed to figure out if the capabilities could meet a real practical need. So right now, Rydberg sensors are around a technology readiness level of 3 or 4. So they're basically undergoing a transition to early applied research. So before starting any research pursuits ourselves, we went through this procedure of evaluating some of the trade-offs in the sensor's performance compared to traditional antenna-based receiver technologies. So we consulted a wide range of potential stakeholders in the technology to understand the potential applications and some of the mission the mission need and the systems requirements for those particular use cases. And that allowed us to better understand, the potential to to identify potential challenges with meeting those system requirements, including in, potential challenges in developing, for example, the laser systems that would be required, and understanding whether it is viable to make the system, as small as it might need to be, or as agile as what's needed for a given use case. So just to give you a slightly more detailed sense of this procedure, we spent about a year going through the methodology that I've outlined here. And it's something that we still continue to do today as we learn more about the sensor and its capabilities. So we spent quite a bit of time looking at, not only the performance metrics of the Rydberg sensor, but also kind of doing a deep dive comparison to, classical competing technologies. And so we looked at some of the key metrics for receivers, which are listed on the upper right here, some of which we understood for the Rydberg sensor, some of which we really didn't initially understand, like gain and linearity. Those are types of parameters that were not well defined when we started working on these Rydberg sensors. So we partnered with antenna and RF experts who could help us make those comparisons. We did modeling and simulation to figure out, what some of the comparative projected performance metrics were, while accounting for performance trade-offs. So one of the big trade-offs that we see with not only quantum sensors, but a lot of technologies in general, is that you can get better performance with a bigger, more expensive system. If you want state-of-the-art sensitivity, you'll need some extra specialized optical components that drive up your size and cost. But if you can live with moderate sensitivity, you can also make a smaller, cheaper system. So there will always be those sorts of trade-offs. And we went through this procedure and, evaluated what we considered to be, some of the projected practical impacts of this sensor for various use cases. And what we ended up focusing in on was the potential of using these sensors for really wideband spectrum sensing with a single, relatively compact sensor device that could also potentially tolerate operating in the presence of noise better than a lot of traditional antenna-based receiver systems. And so when we were satisfied that, we understood a good use case, we formed this interdisciplinary team to start experimental work. We have physicists who could optimize the core sensor, signal processing engineers who can optimize the back end of the sensor and help us process different types of waveforms, RF engineers who continue to help us compare this sensor to classical versions of receivers, and operational analysts who help us, ensure that the research that we're doing is aligned to real, mission needs and capability gaps. So a picture of our tabletop sensor is shown here. It's a bit hard to see details, but at the top you can see, the blue laser light illuminating our atomic vapor cell. And then on the left-hand side here is a big horn antenna that we use to generate the RF signal, so that we can actually, test the sensor with various types of waveforms. So just quickly here, we have two sort of overarching goals in our research. One is to evaluate the practical performance bounds of the sensor rather than the state of the art. And the other is to just help accelerate the transition of this technology out of the lab. So again, we're looking at trying to develop this sensor for very wideband spectrum sensing while operating in a practical noisy environment. I won't go into details about, all of our specific experiments, but I'll just highlight that, we've done a lot of work looking at trying to really rigorously characterize how the sensor would perform in the presence of different types of noise at different frequencies. We've been working on developing a lower swap version of the sensor, both through some of our own techniques, as well as, working to try and advocate for the development of improved laser technologies. And then we've also been doing a lot of modeling and simulation work as well, to better understand how the sensor will perform in practical environments. So then finally, just to wrap up here, these are kind of the two main points that I hope you'll take away from this talk. So firstly, this interdisciplinary systems engineering approach to quantum sensing research and development can enable more efficient technology development. So quantum sensors are not going to be good for everything. But if we can identify early on the specific niche applications where these sensors have a high likelihood of making an impact, then we can help those sensors overcome this valley of death, because we can predict, what some of those systems engineering challenges would be, what we need to do early on to help these sensors transition out of the lab. And show success, in some of those field demonstrations and early technology validation efforts. And then secondly, I really encourage all of you, along with anyone out there who's doing, early research in quantum sensing, to really just talk to as many people as possible who are stakeholders in that research and development pipeline of your focus technology. You should attend workshops and conferences that are adjacent to your field rather than directly in your field. You should walk down the street to the engineering building and talk to someone about challenges with putting your sensor into a smaller box. You might be able to do something early on to help mitigate some of those challenges later on. And you should engage with organizations like the QEDC or other consortia that bring together stakeholders from different fields, stakeholders from academia, industry, government. Those types of efforts will really be critical to helping to advance these quantum sensors and getting them out of the lab and into systems where they could make substantial impacts. And so with that, I'll end, and I'd be happy to take any questions.
Amazing. Thank you so much, Bonnie, for this really wonderful and unique talk.
Of course.
Invite Heisa over to do the Q&A together, and there are many, many questions on the Discord.
Sure.
Heisa is our hardware team lead at WOMANIUM. She's a quantum optics expert previously at the Technical University of Denmark, now at NKT Photonics. And here we have, really many, many questions that I will start to ask right now. Brian from the USA asks, what are the main bottlenecks to commercialization of various quantum sensors? Is it mostly attributable to fundamental physics or enabling technologies like lasers, miniaturized electronics, or is it the funding?
Yeah, so you've hit on all of the main points. I would say that often what we've found is that the biggest challenge for the technologies in some sense will depend on what these core technologies are, but in general what we view is as I think some of the major bottlenecks right now for these atomic and solid state defect systems is in developing lasers that can maintain decent performance outside of a laboratory environment. And then for superconductors, we would love to either, make like cryogenic cooling systems smaller, or of course, make advances in high temperature superconductivity so that we don't need such massive systems to keep these systems cool. So the smaller we can make these systems, the better. And especially, the more ruggedized we can make these systems, ensuring that they can, we can develop them using components that can still operate in the presence of vibrations and temperature fluctuations. That's really critical to getting these out of the lab.
Follow-up question from Brian. How do systems integrators gather resources to make a miniaturized prototype? Because manufacturers are glad to give funding for 1 million, but who wants to make just one?
Of course, yeah, no, that's a great question. And that's something that is, it's not just up to the systems integrators alone. That's something where, there are multiple stakeholders that need to kind of all come together to make this successful. So just, to give an example, for deploying some of these, say, atomic sensor technologies, it would be ideal if we can make more advances in photonic integration of the specific wavelengths of light that we need to operate these sensors. Not all of the wavelengths have, had a lot of funding put towards photonic integration. And so to do that, we really need to bring together either multiple groups that have an interest in, developing this technology so that we can hand it over to, organizations like Sandia that have these facilities that are capable of carrying out that specialized photonic integration for a specific wavelength. But we really need entities from multiple parts of this research and development pipeline to come together and, ideally maybe pool resources, but at the very least, demonstrate the potential impact so that investors are willing to put in the funding to help accelerate this technology and develop, whatever component technologies are not there yet.
Over to you, Haisa.
Can you hear me? Yeah, now it's fine. So maybe a question more in the personal side. So Carolina from Venezuela, she asked, Bonnie, you mentioned that they transition from academia to the industry, right? So what advice would you give to someone who wants to work in the private sector after completing the PhD? Are there any specific steps, strategies you found helpful in navigating this transition successfully?
That's a great question. And I'll note that I don't feel like I'm really particularly working in industry per se, because I still, working for this organization that supports FFRDCs, we still have kind of this advantage of still being able to do kind of early applied research. And there's a lot of, private industry organizations that are a little bit different and have, a stronger focus on, getting out a product as quickly as possible. And the end goal for a place like MITRE and other FFRDCs or university affiliated research centers, often the last thing that we'll do is build a prototype that has, had a successful field demonstration. And at that point, we kind of hand it over to the government and say, we're done. So I think even I'm working in a slightly different field than I would be in industry. But I think in terms of, any advice I would offer is just to essentially leave yourself open to learn as quickly as possible. I don't think that there's anything in particular I would have done differently to prepare in advance for my transition from, my postdoc to coming to MITRE. I was able to learn everything I needed to learn after coming to MITRE. But it is sort of a different environment and a different approach to research, certainly. So I think you should just leave yourself open to learning and talking to as many people as you can once you get to that new environment, so that you can, understand, what sort of that new approach to research looks like, and how you can make the best impact for whatever organization that you're working for.
Now back to some physics. Isma asks, what makes Rydberg atoms so much more suitable for becoming these sensors? How can you measure such broad spectral range? And then there was a question from Julia. Now that the measurements are so sensitive, doesn't it also make you so much more sensitive to noise and how to mitigate that?
Great question. So I don't think I have a great chart that explains this, but I'll try to say as much as I can in words. Essentially, there are sort of two different operating regimes for these sensors. I'll try to answer this quickly because I know we're low on time. But there's sort of a more sensitive regime of operation, and then there's a less sensitive regime of operation. The less sensitive regime allows you to get this very broad tunability. So essentially, you can think of this as, these Rydberg atoms are minuscule electric dipoles. They will be perturbed by any RF field that's passing through them. So there's going to be some change in that miniature dipole anytime there's an RF field of any frequency that passes through them. They may be more or less sensitive to certain frequencies. in general, we're not, because this is a fundamentally different readout procedure, we are able to, we're essentially always making a sub-wavelength sensing measurement. And so it's kind of a completely different principle of operation than antennas that have to, absorb some fraction of power to get a decent measurement. Here, we're making a coherent measurement, which sort of intrinsically allows us to overcome any sort of coupling between the wavelength and the size of the sensor. If we want to make a highly sensitive measurement, we have to work in what we would call a resonant sensing regime, which is, in our case, there are sort of specific discrete Rydberg states that operate at specific energy levels, and there are specific spacings between different Rydberg states. There's a whole array of Rydberg states that we can work with. And if we happen to use want to sense an RF frequency that is tuned exactly to the frequency between two Rydberg states, we can get what we would call a resonant enhancement. It turns out that helps our atoms be extra sensitive to that particular frequency. And so we can make a particularly sensitive measurement if we happen to be looking at one of those specific carrier frequencies. There are ways to tune the atom's energy levels around, actually, to change what those frequencies are, which is great and helps us with that tunability problem. But when we're operating in that, really that resonant regime, we can make a really sensitive measurement. And it turns out that when we're operating in that regime, the atoms do a really great job of rejecting any noise that's outside of what we call a line width. It's kind of a specific spectral window where the atoms happen to be the most sensitive. And the atoms do a great job at just filtering out noise outside that window. So the atoms, they won't behave uniformly for sensing across this whole spectrum. But depending on exactly what you want to do with this sensor, you can make it more sensitive, you can make it better at rejecting noise, and there are ways to kind of tune the sensor around to do better or worse at different frequencies, depending on what you want to optimize.
Sure. Yes, maybe a question from Victor from Mexico. How the Rydberg atoms are fixed in the sensors? Is movement of the sensor a problem?
Sorry, can you repeat that? I didn't quite catch that.
Yes. If the movement of the sensor is a problem, yes, and also how the atoms are fixed in the sensors. And maybe just to complete this question, what more applications you can use Rydberg atoms more than for these sensors?
Oh, sure. So the biggest problem with moving these sensors around is really primarily owed to the lasers. I think the best path forward for mitigating that challenge is to develop solid state lasers that are directly generating light at the specific wavelengths that we need, and also developing good components for photonic integration so that ideally we can integrate everything into solid state waveguides and have as few moving parts as possible. That's really the key to be able to develop a version of this sensor that can operate on a mobile platform. The atoms themselves, right now a lot of the experiments are just housing the atoms in a little glass vapor cell, there's but for future versions of the sensor, we could envision sort of integrating that vapor cell directly into a waveguide, for example. That's something that NIST has done in some of their developments of chip scale atomic clocks. They've developed kind of miniaturized atomic vapor cells for that purpose. And so I'm actually pretty optimistic. I think we can apply a lot of the same developments that have been made in the development of chip scale atomic clocks could apply to miniaturizing this sensor technology. We just need to figure out how to miniaturize and optimize the other laser system that we need to operate the sensor. And then in general, I think the question was, what else are Rydberg atoms useful for beyond just operating as electric field sensors? So there's also a lot of research in looking at the potential for using Rydberg atoms as, for example, quantum memories, which would be, one important piece of a broader quantum network. The really nice thing about Rydberg atoms is they can have a relatively long lifetime. So that's one of the value propositions for using them as a memory. And then there are also a lot of people looking at using them as qubits for quantum computing as well. You'll probably hear about some of that during the course of this program.
Great. And MITRE is actually everywhere. It is also not the first time for WOMANIUM to engage with MITRE. Earlier, 2017, 2018, WOMANIUM worked together with MITRE with the Defense Innovation Board on AI for reverse intelligence and more. Can you share, Bonnie, what are more applications where MITRE has played an important role, but we actually are not aware of it?
Sure. So early on, MITRE is, I think we're 60 years old at this point, roughly. And we actually first started as essentially a spin-off from MIT. That's the MIT in our name. It used to be MIT Research and Engineering, and now we're just MITRE. And early on, we essentially played a major role in developing, deploying, and operating GPS. That was kind of the big initial thing that we did. And our company has just continued to grow since then. We still do, quite a bit of work in that field of PNT, which stands for positioning, navigation, and timing. We do a lot of work there, but as Marlow said, we also have expanded, and we now do a lot of work in artificial intelligence, in cybersecurity. We do a lot of support for logistics, for aviation. It's quite a big company that spans a lot of fields.
And started from MIT. Soon next week, we will have a speaker from MIT on superconducting qubits for one of the most prevalent modalities, platforms for quantum computing, and later on NV centers in diamond for quantum sensing. Really looking forward to that. Bonnie, thank you very much for this amazing talk and for enlightening us in this topic. It was really a pleasure. There are more questions on Discord. We will share some of them with you by email later on.
Great, thank you
very much for being here today.
Thank you.